What if the world you see isn't the only one? What if every choice you've ever made, and every choice you didn't, actually exists in another universe running parallel to your own? This isn't just science fiction. Quantum mechanics, the mysterious foundation of modern physics, is forcing us to rethink what reality actually means. In this video, we'll dive into how quantum mechanics challenges our most basic assumptions and why it might point toward the existence of multiple universes. At the dawn of the 20th century, physics looked almost complete. Scientists believed they had uncovered nearly all the great secrets of nature. Newton's laws had explained motion and gravity with astonishing precision. Maxwell's equations had revealed electricity, magnetism, and light as different faces of the same force. The universe seemed neat, orderly, predictable, a grand machine running on discoverable rules. There were only a few small puzzles left, a couple of stubborn anomalies. Most physicists assumed these would be solved with just a little more effort. Lord Kelvin even declared that physics was finished, with only 2 small clouds on the horizon. But those clouds turned out to be storms powerful enough to rip apart the foundations of reality. One of the first cracks came from light itself. For centuries, scientists debated whether light was a wave or a particle. Newton had imagined light as little corpuscles, tiny particles streaming through space. Later experiments showed interference and diffraction, which seemed to prove that light was a wave, rippling through an invisible medium called the ether. The debate might have ended there, except experiments kept turning up contradictions. At the turn of the century, physicists studying the photoelectric effect discovered something strange. When light shone onto a metal surface, it knocked out electrons, but only if the light had a high enough frequency. Brighter light at a low frequency did nothing, while even a faint beam of high-frequency light could eject electrons immediately. The result defied wave theory. It was Albert Einstein in 1905 who offered the radical explanation: light comes in packets, discrete chunks of energy, later called photons. Light was not only a wave, it was also a particle. This dual nature of light shattered centuries of certainty. The familiar world of continuous waves and solid particles gave way to something fuzzier, stranger, less certain. The implications were staggering. And yet the story didn't stop there. At the same time, scientists were probing the atom, once thought indivisible. Experiments by Ernest Rutherford in 1911 revealed a tiny, dense nucleus at the heart of the atom, surrounded by electrons in orbit. The model looked like a miniature solar system, with the nucleus like the sun and electrons like planets. But classical physics predicted such a system couldn't last. Orbiting electrons should constantly radiate energy and spiral into the nucleus in a fraction of a second. If that were true, atoms couldn't exist at all, let alone build the material universe. Clearly something fundamental was missing. The answer came from Niels Bohr. In 1913, he proposed that electrons couldn't orbit just anywhere. They could only occupy certain allowed levels, quantized orbits with fixed energies. Electrons could jump between these levels, absorbing or emitting energy in the form of photons, but they couldn't exist in between. This strange restriction explained why atoms produce distinct spectral lines, colors of light unique to each element. Bohr's model was clumsy, but it worked. And more importantly, it introduced the shocking idea that energy itself came in indivisible chunks, quanta. The smooth, continuous picture of reality was giving way to something granular, digital, unpredictable. But the real revolution had begun a little earlier, in 1900, with a quiet German physicist named Max Planck. Planck had been studying blackbody radiation, how objects emit light when heated. Classical physics predicted a catastrophe, that a hot object should emit infinite energy at ultraviolet frequencies. Obviously, this didn't happen. Desperate for a solution, Planck proposed that energy could only be exchanged in discrete amounts, proportional to frequency. He introduced a new constant, now called Planck's constant, one of the most fundamental numbers in physics. Planck himself thought it was just a trick, a mathematical fix, but it wasn't. It was the beginning of a new understanding of reality, a door opening to the quantum world. As the 1920s dawned, young physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built on these foundations and discovered rules that would permanently rewrite our picture of existence. Schrödinger devised an equation that described particles not as solid dots but as waves, spread out entities with probabilities rather than certainties. Heisenberg introduced matrix mechanics, a mathematical system that could predict outcomes without describing physical paths. From his work emerged the famous uncertainty principle. You could know a particle's position or its momentum, but never both with absolute precision. This wasn't just a flaw in our measuring tools. It was a feature of reality itself. At the deepest level, nature is uncertain. Events do not unfold with perfect predictability. They emerge from a cloud of possibilities. This was shocking. For centuries, science had been built on determinism. If you knew the starting conditions, you could predict the outcome. Laplace, a French mathematician, once imagined a great intellect that knew the position and velocity of every particle in the universe. To such a mind, the entire future and past would be as clear as a book already written. Quantum mechanics smashed that dream. It said the universe is not a clockwork machine, but a probabilistic dance. Atoms, photons, electrons, they do not follow predetermined paths. They exist as probabilities until measured, and only then does reality solidify into one outcome. Einstein could not accept this. He famously declared, "God does not play dice with the universe." To him, quantum mechanics was incomplete, a temporary stopgap until deeper truths emerged. But experiment after experiment confirmed the predictions of quantum mechanics with uncanny accuracy, no matter how strange it worked. The dice, it seemed, were real. The most baffling evidence came from the double-slit experiment, one of the most famous experiments in science. Imagine firing tiny particles at a wall with two slits. If they were just particles, you'd expect them to pass through one slit or the other, forming two bands on a screen behind. But that's not what happens. Instead, they form an interference pattern, ripples of light and dark, as though each particle went through both slits at once and interfered with itself. It behaves like a wave. But then, if you set up a detector to see which slit the particle goes through, the interference disappears. The particle acts like a particle again, choosing one path. It is as if the particle knows it is being observed. This experiment, repeated countless times, demonstrates the heart of quantum strangeness. Particles don't exist in definite states until measured. They exist in superpositions, multiple possibilities at once. Observation forces them to collapse into one reality. This is not just theory. It has been tested with electrons, atoms, even molecules made of hundreds of atoms. The result is always the same. Reality, at its core, behaves in ways that defy common sense. By the 1930s, the framework of quantum mechanics was complete. It explained why atoms are stable, why chemistry works, why the sun shines. It gave rise to technologies that now shape our world: transistors, lasers, computers, medical imaging. Quantum mechanics was not an abstract curiosity. It became the foundation of modern civilization, and yet no one could agree on what it actually meant. Was reality fundamentally uncertain? Did observation create reality? Were there hidden variables, as Einstein hoped, that would one day restore determinism? Or was the universe even stranger than anyone dared to imagine? The birth of quantum mechanics was not just a new chapter in physics. It was a revolution, one that tore down the neat, orderly universe of Newton and replaced it with something bizarre, elusive, and mysterious. A universe where particles are waves, where energy comes in quanta, where certainty is an illusion, and where the act of measurement itself changes the outcome. A universe that seems to play dice, and yet this was only the beginning. These discoveries opened the door to even stranger concepts: superposition, entanglement, the observer effect, and the radical possibility that our universe is not alone, but one among countless others. The strange birth of quantum mechanics was like hearing the first notes of a symphony we still don't fully understand. There's symphony that continues to play, reshaping not just science but philosophy, and perhaps even our sense of what it means to be real. When most of us think of everyday objects, we assume they exist in definite states. A coin is either heads or tails. A light switch is either on or off. A cat is either alive or dead. But in the quantum world, certainty vanishes. At its core lies one of the strangest, most unsettling principles of all: superposition. Superposition is the idea that a quantum system doesn't occupy a single state until it is observed. Instead, it exists in a blend of possibilities, a mixture of all the outcomes that could happen. Only when a measurement is made does the system collapse into one definite result. This isn't just a metaphor, it's baked into the mathematics of quantum theory. Schrödinger's wave equation doesn't describe a single path or a single outcome. It describes a wave of probabilities, spreading out into multiple potential futures. Every electron, every photon, every particle in the universe exists as a superposition until something forces it to take on a definite identity. The idea is almost impossible to grasp intuitively. Our brains evolved in a macroscopic world of chairs, trees, and planets, where objects have definite properties. But at the quantum scale, the rules bend. A particle can be here and there, up and down, spinning clockwise and counterclockwise all at once. To illustrate this, physicist Erwin Schrödinger imagined a bizarre scenario in 1935. He asked us to picture a cat locked in a sealed box with a vial of poison. The release of that poison is triggered by the decay of a single radioactive atom, a quantum event. The decay is a probabilistic process, a coin flip of nature itself. If the atom decays, the poison is released and the cat dies. If it doesn't, the cat lives. According to quantum mechanics, until you open the box and observe, the atom exists in a superposition of decayed and not decayed, which means the cat, horrifyingly, exists in a superposition of alive and dead. It's not that the cat is secretly alive or secretly dead and we just don't know. The mathematics says it is both simultaneously until observed. Schrödinger himself proposed this thought experiment to highlight the absurdity of taking quantum rules literally. But the fact remains, quantum mechanics works. Its predictions have been tested in laboratories countless times, and the results align with this bizarre picture. Superposition isn't limited to thought experiments. It's real, and we can observe its effects. In the famous double-slit experiment, particles fired one at a time still produce an interference pattern, as though each particle travels through both slits simultaneously. It's only when we measure which path it takes that the pattern vanishes, and the particle seems to choose. So until then, it exists in a superposition of both paths. Superposition has been demonstrated not just with electrons or photons, but with atoms, and even with large molecules made of hundreds of atoms. In principle, there's no upper limit. Entire objects, entire systems, perhaps even entire worlds could exist in superposition. Though in practice, decoherence quickly destroys quantum effects at larger scales. So why don't we see superpositions in our everyday lives? Why isn't your coffee mug both on the table and on the floor? The answer lies in something called decoherence. Quantum systems are delicate. They maintain their superpositions only when isolated from the environment. The moment they interact with their surroundings, with air molecules, heat, light, or any form of noise, the superposition collapses into a definite outcome. In the quantum realm, isolation preserves weirdness. Connection forces definiteness. But this raises deep philosophical questions. Does the collapse of a superposition happen because of interaction with the environment? Or does it require an observer, a conscious act of measurement? Some interpretations of quantum mechanics insist that measurement itself is a physical process, no different from any other interaction. Others argue that observation, perhaps even consciousness, plays a mysterious role in shaping reality. The idea that observation might influence reality directly has fascinated scientists and mystics alike. Could it be that the act of looking, of becoming aware, is what solidifies the universe into a definite form? Or is consciousness simply another quantum system, entangled with the rest? We don't know. But what we do know is that superposition isn't an abstraction. It's a real effect that can be harnessed. Quantum computers, for example, rely on superposition. A classical bit can be a 0 or a 1. But a quantum bit, or qubit, can exist as both 0 and 1 at the same time thanks to superposition. With many qubits entangled, a quantum computer can explore vast numbers of possibilities simultaneously, solving problems that would take classical computers millions of years. The technology is still in its infancy, but it demonstrates how the weirdness of superposition is already reshaping our world. Superposition also lies at the heart of quantum cryptography, where information encoded in superposed states can be used to create communication channels that are fundamentally unhackable. Any attempt to eavesdrop collapses the superposition and reveals the intrusion. Reality itself becomes the security system. But the most tantalizing implication of superposition isn't technological. It's existential. If particles can exist in multiple states at once, what does that mean for us, for our choices, for reality as a whole? Does every quantum event create a branching of possibilities, each equally real? Could there be multiple universes, each representing a different outcome of superpositions collapsing in different ways. This is the seed of the many worlds interpretation, which suggests that every quantum choice spawns new universes, parallel realities in which all possible outcomes are realized. In one universe, Schrödinger's cat is alive. In another, it's dead. In one universe, you pressed play on this video. In another, you didn't. In one, you chose tea. In another, coffee. Each possibility unfolds into its own universe, equally real, equally valid. It's a breathtaking idea, one that stretches the imagination to its limits. But whether or not you accept the many worlds view, the fact remains, superposition is real. It is the foundation of quantum mechanics. It forces us to confront a universe that doesn't exist in certainties, but in possibilities. A universe where particles are not here or there, but both. Not up or down, but both. Not alive or dead, but both are, until we look. Superposition shakes our assumptions about reality itself. It suggests that what we call reality is not a fixed stage, but a constantly collapsing wave of probabilities. It tells us that the universe is not definite until it is observed, that existence is, in some sense, unfinished until it interacts with something else. It's a profound shift in perspective, and as strange as superposition sounds, it has been tested again and again in laboratories around the world. It is not a theory in doubt, it is a fact of nature. A fact that demands we rethink what it means to be real. So the next time you flip a coin, consider this. In the quantum realm, it's not just heads or tails. It's both until the moment you look. And perhaps in some deeper sense, it's both even after. Superposition is the first true taste of how bizarre the quantum world can be. But it is only the beginning. Because if particles can exist in multiple states at once, what happens when they also become entangled? What happens when the fate of one particle is mysteriously tied to another, no matter how far away? That mystery, entanglement, Einstein's so-called spooky action at a distance, is where our journey leads next. In the classical world, reality feels independent of us. The moon is there whether we look at it or not. The sun shines whether or not we open our eyes. A tree falling in the forest makes a sound, regardless of whether someone is listening. But in the quantum world, this assumption is no longer so simple. Here, reality is not always fixed until it is observed. And this idea, the so-called observer effect, is one of the most controversial, mind-bending, and philosophically charged aspects of quantum mechanics. The observer effect emerges most dramatically in the double-slit experiment, the same test that revealed the strangeness of superposition. Recall how it works. When particles like electrons or photons are fired at a barrier with two slits, they mysteriously create an interference pattern as if each particle passes through both slits at once. But when we try to measure which slit the particle actually travels through, the interference vanishes. The particles behave as though they've made a choice. It's as if the act of measurement itself forces the particle to decide. Without observation, it remains in a ghostly blur of probabilities, a wave of potential paths. With observation, it collapses into a single outcome. In other words, before we look, reality is uncertain. When we look, reality becomes real. But why? Physicists have struggled with this question for nearly a century. Is the act of measuring a particle simply a physical process, like bumping into it with a photon? Or does the act of conscious observation somehow play a fundamental role in shaping reality itself? This puzzle led to one of the most profound debates in the history of science. On one side stood Niels Bohr, champion of the Copenhagen interpretation, who argued that quantum mechanics does not describe reality itself, but only our knowledge of it. According to Bohr, particles don't have definite properties until they are measured. Reality is not a fixed stage, but a drama that unfolds only in the act of measurement. On the other side stood Albert Einstein, who resisted this view fiercely. "Do you really believe the moon is not there when you are not looking at it?" he asked. For Einstein, reality had to exist independently of observation. He could not accept a universe in which consciousness was somehow written into the fabric of physics. He famously dismissed quantum uncertainty with the phrase, "God does not play dice," but the experiments kept coming. And again, they seemed to confirm the unsettling truth. Measurement matters. The universe does not reveal itself fully until probed. This led some physicists and philosophers to propose radical ideas. Perhaps consciousness itself collapses the wave function. Perhaps it is awareness, not just physical interaction, that crystallizes probabilities into actual events. This is known as the von Neumann-Wigner interpretation, the notion that the mind is not just a passive observer, but an active participant in reality's unfolding. It's a seductive idea. It suggests that consciousness and the cosmos are deeply intertwined, that we are not merely spectators in a universe of matter, but co-creators of reality itself. It echoes ancient philosophies, from Hinduism's Brahman to Buddhism's dependent origination, where mind and world are inseparably linked. But does science truly demand this? Or are we stretching the meaning of observer? Many physicists today argue that the observer effect does not require human consciousness at all. Instead, it's about interaction. A particle collapses not because a person sees it, but because it interacts with its environment, with photons, with air molecules, with a detector. In this view, observation is just a word for entanglement with the outside world. Reality becomes definite not because of mind, but because of physics. Still, the mystery refuses to die. Consider the delayed choice experiment proposed by John Archibald Wheeler. In this experiment, a particle passes through the slits, but we choose whether to measure its path only after it has already gone through. Astonishingly, the results suggest that the decision to measure seems to retroactively determine the particle's past behavior. It's as if the future choice of observation reaches backward in time to decide what the particle did in the past. This isn't science fiction. It has been tested, and the data matches quantum predictions. The universe seems to know in some sense whether it will be observed, and only then decides how to behave. And so, the observer effect raises profound questions. Does consciousness shape the universe? Or is consciousness itself just another quantum process, subject to the same rules of collapse and uncertainty? Is reality an objective stage, or is it deeply participatory, woven together by acts of observation at every moment? One thing is certain. The observer effect has forced us to re-examine our place in the cosmos. In the classical worldview, we are insignificant. The universe is vast, indifferent, unshaken by our existence. But in the quantum worldview, we might be entangled with the very structure of reality itself. Our act of observing, of asking questions, might be what makes the universe cohere into a definite form. For some, this is empowering. It suggests a participatory universe, one where mind and matter are inseparably linked. For others, it is deeply unsettling. It undermines the very notion of an objective world out there, independent of us. Even today, no consensus exists. The observer effect remains one of the great mysteries of physics. Is it a trick of language, a byproduct of the mathematics, a misunderstanding of what measurement really means? Or is it a clue to something far deeper, that consciousness itself is a fundamental property of the universe, as basic as space, time, and matter? If the latter is true, then the implications are staggering. It would mean that mind is not an accident of evolution, but a cosmic ingredient. That reality is not merely observed, but also constructed. That the universe, in some profound sense, awakens through us. As we move forward in our journey through quantum mechanics, keep this in mind. Every measurement, every act of observation, every moment of awareness might not just be recording reality, it might be shaping it. And if that's the case, then the boundary between science and philosophy, between physics and metaphysics, becomes blurred. We are not just asking about particles and probabilities. We are asking about the nature of existence itself. Next, we turn to perhaps the strangest quantum phenomenon of all, entanglement. A force so mysterious that Einstein called it spooky action at a distance. A connection so deep that two particles, separated by light years, can still behave as if they are one. If superposition challenges our idea of objects, and the observer effect challenges our idea of reality, then entanglement will challenge our idea of separateness. In the everyday world, things are separate. If you put your phone on the table and walk across the room, your phone stays there. If you send a letter to someone in another city, the two of you remain distinct, linked only by the paper and ink. Distance separates, divides, and insulates. But in the quantum world, distance is not what it seems. Here, particles can be entangled, bound together in such a way that their fates are linked no matter how far apart they are. Measure one, and you instantly know something about the other. Change one and the other responds, even across light years of space. This is not metaphor, this is quantum entanglement. and it is one of the most bewildering, most counterintuitive, and most experimentally verified phenomena in all of physics. To understand entanglement, imagine two particles born together in a single quantum event, like twins emerging from the same womb of energy. Their properties are correlated from the moment of birth. If one is spinning clockwise, the other will spin counterclockwise. If one is measured as up, the other will always be down. But here's the strange part. Until measured, each particle exists in superposition, both up and down, both clockwise and counterclockwise. It's only when you measure one particle that its state collapses into a definite value, and instantly the other particle, even if separated by vast distance, also collapses into the complementary state. Einstein despised this idea. To him, it smacked of magic. He called it spooky action at a distance, and he argued that there must be hidden variables, unseen properties baked into the particles from the start that determined their outcomes. Surely the particles weren't communicating faster than light. Surely they weren't linked by some cosmic telepathy. But in the 1960s, physicist John Bell devised a way to test this. His mathematical inequalities could distinguish between a universe governed by hidden variables and a universe where entanglement is real. The experiments were carried out, first tentatively, then with increasing precision. And again the results came back clear. Entanglement is real. The universe does not obey hidden variables. Quantum mechanics, bizarre as it is, stands correct. This means that entangled particles remain mysteriously connected, even across the cosmos. They don't transmit signals faster than light, at least not in any way we can exploit, but their shared state defies the classical notion of separateness. It's as if the universe, at its most fundamental level, is a web of interconnections, not a collection of independent parts. Entanglement is not just a curiosity. It is measurable, testable, and increasingly usable. In laboratories, scientists entangle photons, atoms, even small diamonds. Entanglement has been demonstrated across distances of hundreds of kilometers, with satellites beaming entangled photons between Earth and space. Entire fields of research, quantum communication, quantum teleportation, quantum cryptography, rely on entanglement's strange power. Consider quantum teleportation. No, it doesn't mean beaming Captain Kirk across the galaxy. Instead, it means transferring the quantum state of one particle to another, using entanglement as the bridge. The information isn't copied. It's destroyed in one place and recreated in another. What moves is not matter, but the very identity of the particle itself. Entanglement also promises unbreakable communication systems, because if two parties share entangled particles, any attempt to intercept or measure them collapses the entanglement, exposing the intrusion instantly. This could lead to a future where secrecy and privacy are protected, not by codes or locks, but by the laws of physics themselves. But the most profound implication of entanglement is not technological. It is philosophical. Entanglement suggests that separateness is an illusion, that at the deepest level, the universe is not made of isolated objects but of relationships. The particles are not two, but one system, stretched across space. The cosmos, in this view, is a seamless whole, and we are part of it. This vision resonates with ancient wisdom traditions, which for millennia have spoken of the interconnectedness of all things. Now, physics seems to echo that truth in its own strange language of wave functions and correlations. Yet entanglement also raises paradoxes. If two particles remain linked across the galaxy, does that mean information travels faster than light? Einstein's theory of relativity says nothing can, and yet entanglement correlations happen instantly, with no delay. Physicists have tested this over and over, tightening loopholes, eliminating possible classical explanations. Still, the mystery remains. The resolution seems to be that no usable information is actually transmitted by entanglement alone. The instant link is real, but it cannot be used to send a message. The cosmos preserves its cosmic speed limit. And yet, the fact that such correlations exist at all shakes our understanding of space, time, and causality. Entanglement forces us to consider that perhaps reality itself is non-local, that it cannot be fully explained by events occurring at specific points in space and time. Instead, the universe might be fundamentally holistic, with parts only making sense in the context of the whole. And here's where things get even stranger. Some physicists propose that entanglement isn't just a quirky feature of quantum mechanics. It might be the very fabric of reality itself. Theoretical work has suggested that space-time itself, the geometry of the universe, might emerge from networks of entanglement. In other words, the threads of space and time could be woven from the invisible connections between particles. If true, entanglement doesn't just link objects within space-time, it creates space-time. Imagine that. The distances we measure, the separations we take for granted, might be illusions born from the deeper, more fundamental unity of entangled quantum states. So, what does entanglement mean for us? For one, it tells us that reality is stranger and more interconnected than we ever imagined. It challenges our sense of individuality, suggesting that separateness may be a convenient fiction. It also opens doors to technologies that could transform communication, computing, and even our understanding of life. But at its core, entanglement forces us to ask the oldest question of all. What is reality? Is it made of objects or of relationships? Is the universe a machine of parts or a living web of connections? Einstein may have scoffed at entanglement, but the experiments leave no doubt. Spooky action at a distance is real, and as we peel back its layers, we begin to glimpse a universe where the boundaries between here and there, between you and me, between matter and meaning, start to blur. As we leave entanglement behind, we turn to a deeper question still. What if these strange quantum phenomena don't just describe tiny particles, but the entire universe? Could the cosmos itself be quantum? Could multiple realities, multiple universes, all coexist as part of the grand quantum wave function? This is the territory of the many worlds interpretation, and it might change everything we think we know about existence. When you flip a coin, you expect one outcome. Heads or tails, one real event, one definite reality. That's the comfort of the classical world, certainty. But in the quantum world, certainty vanishes. Remember superposition. A particle can exist in multiple states at once, a blur of possibilities. And when you measure it, the wave of probabilities collapses into a single reality. But what if, and here's the staggering thought, the wave never collapses at all? What if every possibility, every potential outcome of a quantum event actually happens? Not in imagination, but in reality. What if when you flip that coin, the universe splits? In one branch, the coin lands heads. In another, it lands tails. Both outcomes are real, but they unfold in separate, parallel worlds. This is the essence of the many worlds interpretation of quantum mechanics, one of the most radical, most mind-expanding, and most debated ideas in modern science. The many worlds theory was proposed in 1957 by a young physicist named Hugh Everett. Frustrated with the idea of wave function, collapse, the mysterious process by which possibilities suddenly reduce to a single outcome, Everett suggested something bold. He proposed that the wave function never collapses. Instead, it continually evolves, branching into multiple realities at every quantum event. In Everett's picture, the universe is like an ever-expanding tree of possibilities. Each quantum choice, an electron going left or right, a photon passing through one slit or another, a radioactive atom decaying or not decaying, causes the universe to split into branches. Every possibility is realized. None are lost. This means that there isn't just one universe. There are countless universes, perhaps infinitely many. A multiverse, where every possible history, every possible outcome, every possible version of you and me exists in parallel. In one universe, you are watching this video. In another, you paused it minutes ago. In one, you chose tea this morning. In another, coffee. In one, you took a different job, married someone else, moved to a different city. In another, you never existed at all. Every fork in the road, every decision, every quantum fluctuation, all of it gives birth to new universes. It's a breathtaking idea. And it eliminates one of quantum mechanics' most troubling mysteries, wave function collapse. In many worlds, there is no collapse. The mathematics unfold smoothly. The weirdness of superposition doesn't disappear. It's preserved but spread across multiple realities. But if there are infinite universes, why do we experience only one? Why does it feel like we live in a single definite reality? Everett's answer is that we too are quantum systems. When we observe a particle, we become entangled with it. If the particle goes left, one version of us sees it go left. If it goes right, another version of us sees it go right. Each version of us exists in a separate branch of the universe. But because the branches no longer interact, we never become aware of the other versions. From our perspective, reality seems definite. But from the outside, from the cosmic view, all branches exist simultaneously. It's almost impossible to overstate how radical this idea is. Many worlds suggests that reality is not a single thread, but an infinite tapestry, weaving and splitting at every moment. The universe is not one story, but all stories unfolding side by side, and yet mathematically it works. Everett's theory is not a fantasy. It is a direct interpretation of the Schrödinger equation, the core equation of quantum mechanics. Many physicists resisted it at first, dismissing it as extravagant. But over the decades it has gained traction, not only because it resolves the collapse problem, but because it fits neatly with modern developments in quantum computing and cosmology. Imagine the implications. If many worlds is true, then there are universes where history unfolded differently. Universes where dinosaurs never went extinct. Universes where Rome never fell. Universes where Earth was never born. Universes where life evolved in strange alien ways. Universes where you are vastly different, or do not exist at all. And these aren't science fiction fantasies. They are the natural consequence of the mathematics of quantum mechanics, if Everett was right. But here's the catch. If all outcomes happen, what does that mean for choice, for free will, for meaning? If every decision you make branches into all possible versions, does it matter what you choose? In one universe you succeed. In another you fail. In one you live. In another you die. Does that cheapen our lives or does it enrich them, placing each of us within a vast cosmic ensemble of possibilities? Some philosophers argue that many worlds strips meaning from choice. Others say it magnifies meaning by making every choice the seed of an entire universe. Perhaps both are true. There's also the question of probability. In quantum mechanics, probabilities matter. But if every outcome happens, what does probability mean? Everett suggested that probability reflects the measure of branches. Some are thicker, more weighted, more likely to contain observers like us. Others are thin, rare, fleeting. It's not that some outcomes don't happen. It's that we are more likely to find ourselves in certain branches than in others. Then there's the question of testability. Critics of many worlds argue that it cannot be proven or disproven because we cannot access the other universes. The branches are sealed off from one another. If science demands empirical evidence, then how can we verify the existence of parallel worlds? Supporters reply that many worlds is no more extravagant than the collapse postulate, which also cannot be directly observed. They argue that the mathematics is clean, elegant, and consistent, and that rejecting many worlds requires adding unnecessary assumptions. In science, the simplest explanation that fits the data is often the best. And here's where things get fascinating. Some researchers suggest that quantum computers might one day provide indirect evidence for many worlds. A quantum computer explores many possible solutions simultaneously, as if branching into parallel realities to test them. When it delivers an answer, are we glimpsing the computational power of many worlds working together? It's controversial but tantalizing. Meanwhile, in cosmology, the idea of a multiverse has taken root for other reasons. Inflationary theory, the idea that the early universe underwent a period of rapid expansion, suggests that multiple universes may have budded off from the Big Bang, each with different physical constants. Combine this with many worlds, and you get a truly staggering picture. An endless sea of universes, some born from cosmic inflation, others branching at every quantum event, all coexisting in an infinite multiverse. If this is true, then our universe is not special. It is not the only stage for existence, but one among countless others. And we, our lives, our choices, our stories, are threads in a cosmic web so vast that it defies comprehension. But there's a haunting side to this too. If every possible universe exists, then somewhere every tragedy, every nightmare, every catastrophe also exists. In some branch, every worst-case scenario plays out. And in some branch, every dream comes true. The multiverse is neither good nor evil. Here it simply is, an infinite unfolding of possibilities, indifferent to our hopes or fears. So where does this leave us? The many worlds interpretation may never be conclusively proven. It may remain a framework, a way of thinking about quantum mechanics. But even as an idea, it reshapes our understanding of reality. It tells us that existence may be far larger, stranger, and richer than we ever imagined. And perhaps even if we can never touch these other worlds, their existence matters. They remind us that the universe is not limited to our narrow view. They force us to expand our imagination, to think beyond the bounds of one reality. In the end, many worlds is not just a theory of physics. It is a story about possibility, about the infinite branching of reality itself. It asks us to see ourselves not as fixed beings in a single world, but as part of a cosmic symphony of universes, each playing its own variations of existence. And as staggering as this sounds, the journey doesn't end here. Because beyond many worlds lies an even deeper question. Could reality itself be a simulation? Could the multiverse, with all its branching possibilities, be nothing more than information running on some vast cosmic computer? In the next chapter, we step into the strange territory where quantum mechanics meets digital physics and ask if the universe itself is code. By now, quantum mechanics had already pulled the rug out from under our everyday notions of reality. Particles weren't tiny billiard balls. They weren't even solid things in the way we imagined. They were waves, they were probabilities, they were clouds of possibility collapsing under observation. But even that wasn't the full picture, because as physicists dug deeper, they realized something far stranger. What we think of as particles aren't even the most fundamental parts of reality. Beneath them lies something even more primal, something that doesn't just exist in space, but is space itself. This is the world of quantum field theory. Let's rewind. When quantum mechanics first emerged, scientists thought in terms of individual particles, electrons, photons, protons. They imagined them as tiny dots moving through space, each obeying probabilistic rules. That was weird enough, but the more experiments they performed, the clearer it became. Particles were not independent little marbles. They seemed to be manifestations of something deeper, something that extended throughout the universe. Enter the idea of the field. A field is like an invisible fabric stretched across space and time. Imagine ripples on the surface of a pond. The pond is the field, and the ripples are the disturbances that move across it. In the early 20th century, fields weren't new. James Clerk Maxwell had already unified electricity and magnetism into a single electromagnetic field. He showed that light itself was just a ripple in this field. That was a breathtaking achievement. But quantum field theory, QFT, took the concept to an entirely new level. It said, not only light, not only electromagnetism, but everything in reality is a field. Every particle you can name, the electron, the quark, the photon, is not a little standalone object. It's an excitation, a vibration, a localized blip in a universal quantum field. Think of the electron, for example. There isn't one electron field per electron. There is a single electron field that stretches across the universe. Every electron that exists is simply a ripple in that one cosmic field. The same goes for photons, quarks, neutrinos. Each type of particle is a ripple in its corresponding field. What we call matter is just a symphony of fields resonating, interacting, colliding. In this view, reality isn't made of little Lego blocks. It's made of invisible oceans, endlessly vibrating, and the solid world we experience. The chair you're sitting on, the atoms in your body, the stars in the sky, are just emergent patterns in this deeper quantum fabric. This is a radical shift in perspective. Instead of thinking of the universe as things in space, quantum field theory suggests that the universe is space, or rather, the quantum fields that permeate it. And it gets stranger, quantum fields are not static. They are alive with restless energy. Even in a perfect vacuum, where you might think nothing exists, the fields still fluctuate. Tiny virtual particles appear and disappear, borrowing energy from the void, then annihilating each other in the blink of an eye. This seething activity is called quantum fluctuations, and it means that emptiness itself, the vacuum of space, is not empty at all. It is a boiling, buzzing cauldron of potential, forever birthing and erasing. This is where quantum mechanics collides with one of the deepest questions of cosmology. Could the entire universe have sprung from these quantum fluctuations? Could all of space and time itself be the child of a restless quantum field? But before we get there, let's appreciate what QFT has already given us. By combining quantum mechanics with Einstein's special relativity, physicists forged quantum field theory in the mid-20th century. It became the foundation of the Standard Model of particle physics, the most successful scientific framework in history. The Standard Model describes all known fundamental particles and their interactions: the electron, the muon, the neutrinos, the quarks, the force carriers like photons, gluons, W and Z bosons. It predicted the Higgs boson decades before it was discovered in 2012. It explains why atoms have structure, why the sun shines, why chemistry is possible. Yet even in its success, quantum field theory whispers something profoundly humbling: that the world of particles we touch and measure isn't ultimate reality. It's just the visible tip of a much deeper invisible fabric. A fabric that vibrates with unseen possibility. And here's the kicker. If the universe is made of quantum fields, then in some sense those fields are not confined to one universe alone. The math of QFT doesn't forbid the existence of other field configurations, other vacua, other possible universes, each with different properties. In one version, the electron might be heavier. In another, the speed of light might be slower. In another still, the very fabric of physics might be unrecognizable. This is where quantum fields bleed into the idea of the multiverse. If the vacuum itself can take on different forms, then perhaps our universe is just one patch of a much larger cosmic quilt. A quilt stitched together by the restless, infinite possibilities of quantum fields. And the strangest part of all, we are part of it. The particles that make up your body, your mind, your consciousness, they are not independent entities. They are excitations in fields that ripple through the cosmos. In some profound way, you are not separate from the universe. You are woven directly into its quantum fabric. Quantum mechanics has always carried with it a deep mystery, but perhaps none more unsettling than the question of what really happens when a quantum system is observed. In the classic double-slit experiment, an electron seems to travel through two slits at once, behaving like a wave and interfering with itself. Yet, when scientists try to measure which slit it goes through, that wave-like behavior disappears, and the electron behaves like a particle, choosing one path as though the act of observation forces it to decide. For decades, the standard explanation, the Copenhagen interpretation, insisted that the wave function, the mathematical cloud of probabilities, describing all possible states, collapses into one outcome upon measurement. But collapse was never really explained. Why should observation wield such mysterious power? And what happens to all the other possibilities that seemed to exist just moments before? In 1957, a young American physicist named Hugh Everett III dared to challenge this puzzle in a way that would forever reshape the conversation. Everett argued that the wave function never collapses at all. Instead, all possible outcomes of a quantum event are real. Each possibility doesn't vanish, it plays out, but in a different branch of reality. If an electron has two paths, the universe itself splits. One branch contains a world where the electron goes left, and another where it goes right. If Schrödinger's infamous cat faces a quantum mechanism that might kill it or spare it, then in one universe the cat is alive, and in another it is dead. Both outcomes exist, both are real, but they unfold in separate universes that will never meet again. This idea became known as the many worlds interpretation. The implications are staggering. According to this view, the universe we inhabit is not a single line of history, but an unimaginably vast branching tree. Every quantum decision, every coin toss, every radioactive decay, every fleeting fluctuation splits reality into countless versions. Right now, as you listen to this, another version of you in another universe might be listening to something else. Perhaps they made a different choice earlier today, leading their life down another path. In this picture, reality isn't singular. It is plural, an endless multiverse blooming into infinity. And yet the idea remains deeply controversial. If universes are constantly splitting, why don't we feel it? Why does our experience seem so seamless, so consistent? The answer, Everett suggested, lies in decoherence, the process by which branches separate cleanly and no longer interfere with one another. Once a split occurs, the universes evolve independently, locked away from each other. To us, it feels as though only one outcome was chosen, when in fact, countless outcomes live on elsewhere, forever beyond our reach. Critics point out that the many worlds hypothesis, while mathematically elegant, may not be scientifically testable. If we cannot detect or communicate with these other universes, can we ever truly call them real? Are we simply multiplying realities to avoid facing the weirdness of wave function collapse? For many years, Everett's ideas were dismissed and he left academia, frustrated and unrecognized. He would not live to see his theory rise to prominence decades later, capturing the imagination of physicists, philosophers, and storytellers alike. Outside the laboratory, the many worlds interpretation spread like wildfire. It fueled science fiction novels, blockbuster movies, and comic book universes. The idea of alternate timelines, where history unfolded differently, where you made different choices, where countless versions of yourself live parallel lives, became part of popular culture. But within physics, it remains one of the boldest and perhaps most disturbing contenders for the truth of reality. And so the question lingers. If ever it was right, then every moment we live is not the only moment. Every decision spawns new universes. Every possibility is realized somewhere. This challenges not only science, but philosophy, ethics, and even the meaning of identity itself. Are we unique beings or just one branch among infinite others? Do we truly choose our paths, or do we merely discover which branch we inhabit, while countless other selves take the roads we did not? The many worlds hypothesis does not resolve the mystery of quantum mechanics. It deepens it. But it forces us to confront a possibility more audacious than collapse, more haunting than uncertainty, that our universe is not the universe. It is one story among infinite others, all unfolding together in a multiverse beyond imagination. If the many worlds hypothesis is true, then reality is constantly splitting into countless parallel universes. Each universe is sealed away, evolving along its own path, forever hidden from the others. But is that really the end of the story? Or could there be strange, subtle ways that universes might still whisper to each other? To answer this, we turn to one of the most baffling phenomena in quantum mechanics: entanglement. Entanglement occurs when two particles become linked so deeply that the state of one cannot be described without the state of the other, no matter how far apart they may travel. Measure one particle's spin, and the other's spin is instantly determined, even if it's light years away. Einstein called this spooky action at a distance, and for good reason. It defies our ordinary sense of locality and cause and effect. Yet countless experiments have proven entanglement is real. It is not science fiction. It is a measurable, repeatable part of our universe. Now, if entanglement can link particles across vast stretches of space, could it also extend across branches of reality? In other words, when universes split, do entangled particles carry some lingering connection between those branches? Could there be cracks in the walls of separation, where the multiverse is not so sealed after all? Some theorists have toyed with this idea, imagining that entanglement might be a kind of bridge, not only across space but across universes. The thought is provocative. Perhaps the strange correlations we see in entanglement experiments are not confined to one universe, but instead reflect deeper patterns that stretch across the multiverse. In this picture, when you observe one entangled particle here, its twin is not only determined in our world, but also in all the parallel worlds branching alongside us. But mainstream physics remains cautious. Decoherence theory tells us that once universes split, they do not interfere. The branches become mathematically orthogonal, separate realms with no chance of crossing paths again. If that is correct, then entanglement still operates, but only within one branch, not across them. In this view, our universes are like parallel lines that never meet, forever isolated, forever apart. Yet the possibility is too tantalizing to ignore. If even the faintest interaction between universes were real, it would upend everything we know. It could explain why quantum mechanics seems so strange, as though reality were being shaped by more than just our universe. It could hint at ways to detect or even communicate with other worlds. Some researchers have speculated about experiments that might catch glimpses of interference from other universes, though so far, no evidence has emerged. And then there is the more radical speculation. What if consciousness itself is somehow entangled across universes? What if the reason we perceive only one outcome is not because the others disappear, but because we, as observers, are entangled with one branch at a time? In that case, awareness might act as a thread weaving through the multiverse, attaching us to one reality while countless other versions of us experience the others. This remains speculative, but it stirs questions about identity and perception that go far beyond physics. Whether or not universes can truly interact, entanglement teaches us one crucial lesson. Reality is not as divided as we once believed. Space and time are not barriers to connection. What looks separate may, on a deeper level, be inseparably linked. And if that's true within our universe, then perhaps, just perhaps, it could be true across the multiverse as well. For now, the idea of entangled universes remains a mystery, perched at the edge of science and imagination. But it invites us to keep asking questions, to look deeper, and to consider that the walls between worlds may not be walls at all, just veils waiting to be lifted. At the heart of modern physics lies a profound tension. On one side stands general relativity, Einstein's magnificent theory of gravity, which describes the cosmos on its largest scales, the motion of planets, the birth of stars, the bending of light, the expansion of the universe itself. On the other side stands quantum mechanics, the strange probabilistic framework that governs the tiniest particles, dictating how atoms, electrons, and quarks behave. Both theories work brilliantly in their own realms, but when we try to bring them together, they clash like oil and water. This conflict becomes unavoidable in places where the very large and the very small collide, such as at the center of a black hole, or in the first moments after the Big Bang. In these extreme conditions, relativity's smooth curves of space-time and quantum mechanics' jittering uncertainties must both apply, yet they refuse to merge. It is as if the universe is telling us, you are missing a deeper truth, and that missing truth is what scientists call quantum gravity. Quantum gravity is not one specific theory, but a quest, a search for a framework that unites the laws of the cosmos with the laws of the microscopic world. If found, it could reveal the most fundamental layer of reality, the hidden architecture beneath both space and time. Some believe that this theory could even explain why the universe exists at all, and whether multiple universes are not just possible, but inevitable. One of the leading candidates is string theory. String theory proposes that the fundamental building blocks of reality are not particles, but tiny vibrating strings, far smaller than an atom. The vibration patterns of these strings give rise to the particles we know, electrons, photons, quarks, much like different notes on a violin string. What makes string theory especially enticing is that it naturally includes gravity, something that other quantum models struggle to achieve. And beyond that, it suggests that our universe might require extra dimensions of space, hidden layers of reality, curled up so tightly we cannot see them. Another contender is loop quantum gravity. Unlike string theory, it does not replace particles with strings, but instead reimagines space-time itself. In this view, space and time are not smooth and continuous, but made up of tiny discrete loops, woven together into a kind of fabric. Just as matter is quantized into particles, space itself is quantized into grains, unimaginably small but finite. If true, this would mean that reality is not an endless continuum, but has a smallest unit, an atom of space. Both approaches remain unproven, but both suggest that the universe is stranger than we currently imagine. And importantly, both open the door to the possibility of multiple universes. String theory, in particular, predicts an enormous landscape of possible universes, each with different laws of physics, each corresponding to a different way the extra dimensions could be shaped. If our universe is just one among this cosmic landscape, then the multiverse is not just possible, it is unavoidable. But quantum gravity is not only about alternate universes. It is about answering the most basic questions. What is space? What is time? Are they fundamental, or are they emergent, rising from something even deeper? Some physicists now suspect that space-time itself may not be primary at all, but a kind of illusion created by entanglement. In this radical view, what truly exists is a vast web of quantum information, and space-time is just the geometry that emerges when that information organizes itself. If that is true, then the universe as we experience it, the 3 dimensions of space and 1 of time, may be just a shadow of a more fundamental reality. This search is not merely academic. Quantum gravity touches the edges of human understanding, from black holes that consume everything, even light, to the question of what happened in the first fractions of a second after the Big Bang. Without it, our picture of the universe is incomplete. With it, we might finally understand whether the multiverse is a wild fantasy or a concrete prediction of nature's laws. For now, quantum gravity remains a frontier, a place where our equations break down, where mystery reigns. But it represents the next great step in the human journey, to comprehend reality itself. And if we succeed, we may discover that what we call the universe is only a small piece of something far larger, far stranger, and far more beautiful than we can yet imagine. For centuries, science has been humanity's torch against the unknown, peeling back layer after layer of mystery. We began by charting the stars, measuring the earth and discovering the laws of motion. Then we uncovered the invisible world of atoms, the dance of forces, the machinery of life itself. But quantum mechanics, the physics of the very small, has forced us to confront questions that are not just scientific, but profoundly philosophical. At its core, quantum mechanics tells us that reality is not fixed and definite, but fluid and probabilistic. Objects are not solid little marbles, but clouds of possibilities, existing in superpositions until observed. This single insight has shattered our old assumptions that the universe is clockwork, predictable and objective. Instead, it suggests a cosmos that is flexible, indeterminate, and deeply intertwined with observation itself. But what does that mean for us? If the universe is not a single path but a branching web of possibilities, then our sense of uniqueness and certainty begins to dissolve. In the many worlds interpretation, every choice we make, every roll of the dice, every breath we take, may exist in parallel versions of reality. Does that cheapen our existence if countless versions of us live elsewhere, or does it elevate it, showing us that we are part of something unimaginably vast? Then there is the question of meaning. If multiple universes exist, then our universe might not be special at all, just one among an infinite variety. The laws of physics we observe may not be universal truths, but simply the rules of our local branch. That raises unsettling questions. Why are we here in this particular universe? Why do our laws permit stars to shine, planets to form, and life to emerge? Some physicists point to the anthropic principle. Perhaps we find ourselves here because only in a universe like this could beings like us exist. But for many, that answer feels incomplete, as if the universe is teasing us with a secret just beyond our reach. Quantum mechanics also raises questions about consciousness itself. If observation plays a role in shaping reality, what does that say about the mind? Are we passive witnesses to a universe that unfolds around us, or are we active participants in its creation? Some argue that consciousness is deeply woven into the fabric of quantum mechanics, that our awareness is not just a byproduct of the brain, but a fundamental piece of reality itself. Others reject this idea, warning that it confuses mystery with mysticism. Yet the debate lingers, reminding us that the line between physics and philosophy is thinner than we once thought. And beyond science and philosophy, there is the human dimension. For thousands of years, we have looked to the stars and wondered where we fit in. Quantum mechanics expands that wonder to an unimaginable scale. If we are part of a multiverse, then our existence is both humbling and extraordinary. Humbling, because we are not the center of reality. Extraordinary, because the very fact that we can ask these questions, that lumps of carbon and water, arranged by chance and chemistry, can ponder the fabric of existence, means that the universe has, in some sense, become aware of itself. The search for quantum truth also invites us to reconsider how we live. If reality is uncertain, then perhaps the meaning of life is not fixed but created. If universes branch with every choice, then perhaps our choices matter more than we realize. Not because they determine everything, but because they shape the world we, here and now, inhabit. In a multiverse of possibilities, this branch, this life, this moment is still ours, and that makes it precious. As we close this journey, we are left not with answers, but with awe. Quantum mechanics may never give us certainty, but it gives us something even more profound: wonder. It reminds us that the universe is far stranger, far richer, and far more mysterious than our ancestors ever dreamed. And perhaps in the end, that is the gift of science, not to solve every mystery, but to expand the horizon of what we know is possible. Because when we ask, what is reality? Or do multiple universes exist? We are not just asking about physics. We are asking about ourselves, about who we are, where we come from, and what it means to be alive in a cosmos that defies comprehension. And so the journey continues. We stand at the edge of knowledge, staring into a quantum sea that stretches into infinity. We may never map all its depths, but in the act of exploration, in the courage to wonder, we find meaning. For as long as we keep asking, the universe will keep whispering back.